Hello guys, welcome back. Right, today we're gonna finish this chapter for word embeddings. And then we, because it's only a couple of slides left, and I have updated these slides for word embeddings by adding some a couple of more slides of using word embedding, using embeddings in PyTorch. Let me go to the Canvas page for that. Right. So on the Canvas page. If you go to the module 12, word embeddings, then the PDF file is updated. So if you download it now, you should be able to see some extra slides with PyTorch usage of embeddings. And you can also see this new module 13 called Deep Contextualized Representation. And that is the content I will cover. We will talk about, we will go through after the word embeddings is done. Okay, so in this deep contextual representation, we will introduce a couple of more techniques that are kind of related. Actually, it's very closely related to the word embeddings, but it offers a more, it provides a more sophisticated way to model semantic meanings for words within sentences. Okay, so we will do the word embeddings today first, and then we will also start the next chapter as the new something new today. Okay. All right, and last time we ended here. We have covered that this glove method for training word embeddings, right? But in overall, this is a general idea of the designing of this glove model, which is to minimize the joint cost function, which will makes the words that appears a lot together will also be close in semantic spaces. Okay, and it turns out a very successful model. And for this glove, both this glove and the word2vec model, you are actually able to find there are a lot of pre-trained embeddings available for such kind of models. You can download it from these projects websites, and these are usually nowadays the basis for a lot of baseline models, for a lot of NLP models that directly use the pre-trained word embeddings as input. So we will cover that later when we enter the PyTorch embedding introduction, because it is so commonly used. It is such a widely used technique nowadays. Okay, so before we talk about PyTorch, let's look at the final slide here. It's about how we evaluate the qualities of word embeddings. Okay, so there's more than just one way of evaluating the intrinsic evaluation. So here's just one task, which is the semantic similarity or semantic relatedness. And the idea is very straightforward. So first of all, we need to keep in mind that word embeddings is just a way to, assign a word a dense vector, right? And the assumption is that these dense vectors should be encoded with the meanings of that word, right? So we have this first word is book, the second word is library, and the embedding model should assign the book with a vector called E of book, right? Also assign the library another vector E of library. So once we have two libraries, once we have two vectors, how do we know that these vectors are good, right? So one way of evaluating is that we can measure the cosine similarity or cosine distance between these two embedding vectors, right? And this will give us this D1 score, right, which is listed here. Okay, and this D1 score is kind of a index of how semantically apart or semantically related these two words are, right? And for this particular example, we know that there are books in library, so a model, a reasonable model, a model that makes sense should able to capture this semantic relatedness, right? So, so we will basically compare the D1 with the scores that we obtain from some human subjects, from some human judges. So, like we can do this online through Amazon Mechanical Turk, which is a platform for crowdsourcing projects. Like we have hundreds or even thousands of people rate how semantic related the word book is to library, right? And for example, the score returned by the human judges are 7.46, right? And then we can do this for multiple pairs of words like bank, money, wood, forest, right? Professor, cucumber. So this fourth example is and a counterexample, right, of very little semantic relatedness can be found. So like we want, the general principle is that we want the scores from the human subjects are, so I should say the other way around. We want the cosine distance or cosine scores returned by the model to be as close as the human scores as possible, right? Because we want the models to learn from human knowledge, right? So ultimately, we want the cosine distance to mimic the judgments made by human subjects, right? So now, how close these two columns of scores, the red column from human judge and the green column from the cosine measurements, we want these two columns as close as possible. And this closeness can be measured by the Spearman's correlation between these two columns. Okay, so we would argue that a good model should have better Spearman's correlation score. And on the other side, if the Spearman's correlation is not that high, right, then we assume that the models can be better, right, can be improved. All right, so that's something about how word embeddings can be evaluated. So everything so far are on the paper, right? We have equations describing the word-to-vec, how word-to-vec is constructed, how we come up with the distributed representation for words. And then let's enter the parts for some engineering details, okay? I think nowadays, the word embeddings technique are quite ubiquitous, and both PyTorch, TensorFlow, or other frameworks, they provide really convenient implementations, how you can quickly pick up those embedding vectors, how you can quickly load, how you can quickly evaluate those embeddings, and use them as the inputs for the next, for the downstream NLP models or NLP tasks. All right, so the key components in PyTorch is something called torch.nn embedding with a capital letter, okay? So this one, you can think of it as a collection of parameters, right? So this is an extremely simple example because we assume that we have only 2 words in our vocabulary, and we want to use a 10-dimensional vector to represent 1 word, right? So for example, if I initialize the embeddings in such a way, it will create a random embedding vector for us, in which the numbers are randomly are sampled from basically a normal distribution. Okay, so if you look at the weights for this embeds objects, it's basically a 2 by 10 tensor. Okay, each row is a 10 element vector, right? So that is word 1, right, and word 2. Okay, so these are the vectors that you can use as if they are word embeddings. Okay, but it's just a random initialization. We didn't start training the model yet, right? But you will see that it allows for a lot of flexible operations on top of this embedding objects. All right, that's the first step, right? And you have the flexibility to determine the number of rows. Okay, so the first quantity, basically the first quantity is the number of the size of your vocabulary. If you have 10,000 words in total, then this quantity should be 10K, right? And the next dimension, which is the size of your embedding vector, right? Typical values are like 100, 200, 300, even 500, right? So these are just custom numbers you can use, right, in order to initialize the parameters for you. Okay. So one technical detail you may want to notice on this slide is that it has such a property, such an attribute requires grad equals true, right? So this is something, hopefully this reminds you of something about the characteristic of PyTorch. So everything that is part of the computational graph, everything that are considered as parameters or part of the model must actually have this requires gradients, not graduates, but requires gradients as set to truth, right? So that means these numbers are actually parameters, and those numbers can receive gradients. It can be upgraded, and the values can actually be automatically computed by the engine, by the PyTorch engine. Right, that's for embeddings. And then in Python or in the workflow of PyTorch machine learning tasks, when we are dealing with language data, we need to convert the data types properly, right? So with strings, so the raw data for natural language are basically strings. In Python, it's the string objects, and a typical operation is that we need to convert those strings to indices, to integer numbers. Okay, so for example, here we will need to manually construct some dictionary-like data structure, right? So of course, here we just type in those keys and the values manually, but in practice, we will need to use some code to generate this. And also there are third-party packages that help you accelerate this process. But basically the idea is the same, that you need some dictionary data structure to store such a one-to-one mapping relationship. You want to map the string which is the word to a number, right? So in this case, this word hello is mapped to the integer number 0, and the word is to the integer number 1, right? So that means whenever we saw the word hello again, we can represent it with the integer number 0, right? Which is necessary because eventually, ultimately, we want to convert each word into a vector, right? But as we have seen in the previous slide, the vectors are stored in the table, in the embedding table, and each row for that table is actually a vector, right? So we need to use the row index to access each word vector. So of course, we will need to first convert a word into an index, right? So that is a necessary step. So in this case, the sentence we show here is 3 words, basically, right? It's a long string, and we can split it into 3 words, which is hello, hello, and world, right? So given this word to index objects, we can convert it. We can convert the words into indices, right? So with this code, we convert each word in the words into its indices, which is 0, 0, and 1, right? So that is much closer to what we need, but it's not yet the final form, right? So the next step is a very typical PyTorch operation. Okay, it is to convert the raw data type, which is a list of integer numbers, which is the inputs here, and convert it into a tensor. Okay, so this tensor object is a PyTorch data structure, data type, right? And we can specify the data type to be torch.long, and this long means long integers, and this is just a convention in PyTorch, or it's a rule in PyTorch, that the number that represents word indices should be long tensors. Okay, and the advantage of a long tensor, of a long integer number, is basically that it covers a larger range, right? Because sometimes you can have a lot of much larger vocabulary size, right? So that is just some trivial details. But anyhow, you need to convert the indices, which is primitive type, a list of primitive integers, into this tensor object, right? So now the tensor object looks this way. Basically the values don't change, right? It's just a wrapper of tensor object, right? So the next one, we're almost there, right? We are now finally ready to use this indices tensor to access the embeddings vectors, right? Remember the embeds objects, right, that we defined at the beginning. So now we can use these embed objects as a callable, as if it's a function, right? And we use the indices in tensor as the inputs, so that it can access it will return the embedding vectors for each index in the indices tensor for us, right? So if you look at the shape of this embedding vector, so this object's EMB vector object, it will be in such a shape. It will be 3 by 10, right? So the meaning of this 3 by 10 is very clear, right? Because we have 3 words indicated by these 3 indices. Each word is represented by a 10 dimensional vector. So in total, it will be a 3 by 10 tensor returned. Okay. All right. So this embedding vector will be something we can use. For example, we can use that as the inputs for some classification models, or for some RNN models to do the task we want to do. Okay. So yeah, that is some basic grammars in PyTorch. Okay. All right. So embeddings, you can think of them as learnable parameters. For example, just like the weight matrix, in linear, right? It comes with the learnable parameters. So if you look at the weights of it, right? This is just exactly what we have shown before. And this required graduate equals true, right? So it means that we can use gradients to compute the, to update those parameters. Okay, and those embeddings returned is a tensor, which means that you can just apply any other operations you would like to those tensor objects. For example, we know that the EMB, the embedding object, is a 3×10 tensor, right? So a typical operation such as summation, right? So this time, the first line of code, we have called the built-in function from Python, right? So that is doable. If you use summation on EMB, it will return basically it will basically reduce that 3×10 vector, 3×10 tensor into a basically none-by-10. It's basically a 1×10, but in this case, the first dimension is gone. It's basically reduce the first dimension, right? And you can also increase the first dimension to 1, right? So these are just randomly selected examples here, okay? And you can also, if you are you trust the summations from PyTorch more, then you can use the torch.summation and explicitly specify the dimensions to be reduced, and it will result in a also again the same value as the first example, right? But this time it's just a different function used. Okay, so those operations can be very you have a lot of freedom in selecting which operations you want to place on top of those vectors. All right, and because we said the embeddings are learnable parameters, they are part of the computational graph. So whenever you put some operations on the inputs on the embedding vectors, the corresponding backward functions will be recorded, will be memorized as part of the computational graph. Okay. All right. So that is the infrastructure, basically infrastructure in PyTorch that will enable you to play with embeddings around in your code. Okay, and because nowadays we seldom train word embedding models from scratch. It's like, because it's been there for a while, and the computational resource that people have shared in the world is a very useful resource now. So we don't need to train everything from scratch. And because to prepare a good training data is takes a lot of time, takes a lot of selection. People put effort into that, and so the embeddings trained by different people can actually share it across different tasks. Okay, so like people have used data sources like Wikipedia page, which contains gigabytes, even terabytes of text data. And using such a big training data sets, people can train word embedding models that can have amazing performance in text inference tasks, for example. Then we can directly copy those word embedding vectors directly for the usage of other tasks. Okay, so the pre-trained word embeddings, they usually look like this way. For example, so these screenshots that I have shown here is something I think I trained from a Wikipedia page, but you see it's it's on the Chinese subsets of Wikipedia in Chinese language. So the entries here, the first column is the entry, which is the Chinese character here. Okay, and if you, so this format is a pretty standard format used by, first proposed in Word2Vec, and also later on the researchers basically follow this format so that all the code are as compatible as each other, right? So it's basically the first row. If you look at it, it has the information about this embedding data. It contains basically 12,000, almost 12,000, no, 122, sorry, 122,000 words. So, you know, it's a lot of words, a lot of unique words in this in the vocabulary, in the training data. Okay, and the second 300, which is the size of the dimension of the embedding vector, right? So for the first row, it is the first word, which is this special symbol, right? /s. So this is a special case, a special symbol for the end of sentence. Okay, and because how the data are organized in training a Word2Vec model is that you need to append a end of sentence token to each sentence, and then you put each sentence as a row in the training data, right? So the end of sentence is also considered as a special token, right? But the values are very unique. The values are special values, which are all zeros. Okay, so you see a lot of zeros. Those zeros are just the means that it's not trained, means that the values, the meaning of this end of sentence is not trained. Okay, and from the third row on, it contains the concrete values for each word, right? The first character has such a vector that encodes the semantic meanings of it. Okay, so I think these values are already normalized, I think, right? It's already normalized, which means they are scaled to a vector that has the unit length, that has which is not an original value, but it's a normalized value, which means it's more useful, more stable in semantic inference tasks. Okay, so and one more thing I want to mention is that, okay, so you see the format of the embedding. It's basically a text file. So it's a very primitive way to save data because it will take a lot of space if you store everything in the text formats. And of course, you can compress this data, like to save it into a binary form. You can encode this data, and I think different packages will have a lot of different ways to save or to store this type of embedding data. And if you are doing experiments with this, I think typically what you can try is to write some custom script, some custom Python code to, for example, read this text file and read each line and separate each line into a text entry and a 300-dimensional vector, right? Convert it into a NumPy vector, and then you can basically read everything into a whole NumPy vector. For example, a NumPy array. For example, it can be 123,030 by 300 NumPy array. Okay, so that can be a next step for your usage, right? So this whole array contains all the vectors for all the vocabulary in the data, right? So that is something that can be easily achieved. Okay, so I mentioned this because given the embedding file, we want to load it. We want to load it into our model. We want to copy this NumPy array into our model because we want to directly use it to initialize the NN embedding parameters. Okay, so for example, in the code here, you see this is from the code for a LSTM based text classification model, right? So within the definition of this LSTM model, right, we defined something called embedding. So this is the embedding objects, right? We initialize with this NN embedding, which we specify with vocabulary size and embedding size, right? So after this line of code, we know that the embedding is there, but it's random. It's just randomly generated. So those initial embeddings doesn't contain any useful information yet, because each row are just randomly generated embeddings. So we want to overcome that. So what we're going to do is to, when we initialize the model, we pass along the embeds weights as part of the arguments, for example. And then we will use that embeds passed in arguments to initialize this embedding object by calling some functions provided. Okay, it's called from pretrained, right? So as long as these embeddings, so these embeddings is in the compatible formats. For example, it should have vocabulary size rows and embedding size columns. Then this is we say a compatible embedding. Then those values in the embedded weights will be copied to the embeddings objects, right? Which means that we are reusing the embedding vectors from other people, right? So that will be the a very first step before using in initializing the LSTM models. Okay, so because we mentioned the LSTM models here, let's draw some connections between word embeddings and the LSTMs. Okay, so actually these two kinds of techniques, they are so commonly coupled, they are so closely coupled. Okay, and previously we when we talk about RNN models, all the examples we show actually use one-hot encodings as inputs, right? If we don't use embeddings, then at each time step, so this is a figure for a bidirectional RNN network. So for each time step, the input x1, x2, x3, x4, they are one-hot encoding vectors for each word, right? But we want to use embeddings rather than one-hot encodings, because in word embeddings, they carry concrete meanings for each word, so that the inputs are now not random one-hot vectors, right? So for example, here we can replace the one-hot encodings with the embeddings for the first word and second word, third word, and the last word. Okay, so that the models can use the semantic meanings encoded in those embedding vectors, so that to better represent the whole sentence, better understand the semantic meanings between different words. Okay, so in order to doing such a to implement such a model that takes inputs, takes the embedding as inputs, then we basically need to set up the LSTM model better. For example, the way that we define the LSTM model should, of course, make sure that the input size is now not the one-hot, not the vocabulary size, but instead it should be the embedding size, right? Because the input is no longer the one-hot vectors, but embedding vectors. So we can do this, of course, right? So that it matches our expected inputs, okay? And in our forward function, when we define the LSTM model, we also need some extra steps, right? Because the inputs, the LSTM model will take some input sequences as input in a mini batch, right? So this input, if you examine the shape of it, it's usually in this shape. It's batch size by that size. This is the maximum sequence length, because anyway, it's a mini batch, right? So the left end there, they meet the same end. So it's basically a how to say, a two-dimensional array in tensor in long term in long tensors. So it should be batch size by max sequence length. Okay, max sequence length. So in a language task, it is it's a innate problem or innate issue that's we have multiple sentences, but the actual lengths for each sentences are different. So how do we fit that, like for example, 128 sentences of different lengths into one batch, right? So for those shorter sentences, we need to pad the remaining elements in that row with some special tokens, right? So we need to do that, and fortunately, we have PyTorch have the N&U tools that have such a function to automatically pad the input for us, right? So as long as we supply another sequence that tell us the actual length for each row, okay? So this sequence length contains the length information for each row in that input sequences. Okay, so we just feed that into this function, and of course, more importantly, is the first row, right? So the input sequences is just a long tensor. Okay, it is the indices. The word indices in a tensor format. So we should first convert it into some embedding, right? We just call the embedding. So now X is in this dimension. It's a three-dimensional cube. Okay, it's batch size by maximum sequence length by embedding size. So this embedding size can be, like, for example, 300. So now this X is a very large volume. Okay, it has now 3 dimensions, right? The third dimension has that many long vectors. Okay, so this X needs to be packed by calling this need to be padded by this default function, internal functions. Okay, and then this packed values will be fed into the LSTM, right? So we have that many 2 steps before calling this LSTM model at this step. Okay. And then the outputs and the last memory cell will be used to, for example, to some classification tasks. Okay, so these outputs will be, for example, will be returned, right, by the model. Okay, so yeah, that is some code examples of showing how word embeddings can be actually used together with a RNN LSTM model. Okay, so I am currently preparing the homework for word embeddings, and I don't think we're gonna use embeddings with LSTMs this time, but we're gonna look at how embeddings can be fed into a simpler model, which is a fully connected, which is a regular neural network model. And we will use that to basically train a very small model based on a very small toy data. Okay, but we will get some hands-on practice on how to use embedding vectors. All right, I think that's the last slide. All right, so let me stop recording.